Junior Epstein, so I'm obviously butchering your name, J.R. Epstein, whatever, I don't know how to say these names. The random question is, how does HTM deal with predicting a pattern that starts partway through? Oh, that's easy. Okay, so you think about sequences. Maybe I should turn this on. Let me just do it on the whiteboard. I have to turn this. So the question, so you hear a song, right? Say you know already 100 songs. I mean, you know more songs than that probably. Probably know thousands, maybe tens of thousands of songs. If you're a musician, certainly. So all those songs have like a beginning and they go on for a while and they end. Here's this one maybe shorter, this one's longer, but essentially they're sequences of patterns, right? And they all have a beginning some point. And this is like any type of sequence. Has a beginning and an end and a bunch of stuff in between it that changes over time. And what's changing is the state of things, right? The state of, in this case, it's the state of the song, the melody, but you can think of spatial state changing over time. And what HTM does is it creates this structure within the mini column and the cells within the mini column. This is not a neural network unit, by the way. This is this is not a neural network layer if you're coming from the machine learning world. This is a mini column, and these are pyramidal cells, not point neurons. These are pyramidal cells that have distal connections and proximal connections. Okay, so that's a big difference if you're coming from the machine learning world. It's a totally different structure. It allows this temporal linking of sequences, right? So if you were trying to learn these songs spatially, you could give them each sort of a fingerprint and a spatial fingerprint. This is, I think, how deep learning currently tries to memorize songs. They might batch it, cut it up into pieces, and then store each of those as sort of a fingerprint of that part of the song. So when you start listening to a song, you start recording it, you process that, and then compare in the same way you process your other songs that you train the network on, and then you compare it essentially. I'm not the expert, so I'm assuming this is how they do it. This is how I would try to do it. Compare it to the batches that you did and find the songs that are most similar. And once you have a few, you can use brute force to figure out what it is. But that's not the way your brain does it. That's not the way sequence memory does it. So if you think about like the note C, let's say C in the A, B, C, D, E, F, G scale. There might be C's all over. This song might have a ton of C's. This might be in the key of C. So there's C's all over the place. There may be a few C's here. Some might not have any C's, right? So that note, that C, could be, if all you had was a C and you just heard bing, I can't sing a C, okay, I don't have perfect pitch, but if you just heard a C, whatever, you could not think of anything, any song that was in, because unless it was like Beethoven, like bum 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 bum, I don't know, maybe that would trigger that because it's such a hard beginning of a song. But if it were just any C in the middle of the song, you'd never come up with one. If you had two, hey Mark, I'm talking about how sequence, how you can have like start in the middle of a song and match a sequence a song that you know, like technically. If you have two, like an interval in music, they call it an interval. If you have two notes, C to an F, for example, that transition now has meaning, right? So a C to an F might only happen in this song here and maybe once there. So now you've narrowed it down. So that transition C to F, these mini columns will retain. So if this is a C, that this might represent C after F. Another cell in here, if it's active, it might mean C after E. Okay? So as soon as you identify like two bits in the sequence, you can start narrowing it down in this fashion by sort of doing this broad. It's sort of like a quick, I don't know, I hesitate to call it a search, but it really sort of is a search. You can search your whole memory space just by performing a union, right? So you can perform a union of the representations between one note and the next, or that transition itself, and then compare it to the union of things that you've seen and narrow things down. So I think that's generally how you do it. And temporal memory works that way. So if you learn a bunch of sequences and then you play CE, it will return all the bits that represent all the songs. I mean, if you were doing object pooling, right? But it would basically give you all the locations. This is what temporal memory would do. It would give you this, and this, and it would give you probabilities for each one. So you could predict where you're at, what's going to be next. You know, the problem with temporal memory is because we don't have a way to pool over this and identify the sequence, like the object identification of the song that we're in, the sequence that we're in. We might know where we're at and what's coming next. Excuse me. We might know what the system itself might make a good prediction of what's coming next, or make interesting anomaly indications, but we can't tell which song we're in, right? So that's one thing that's tricky. That maybe that answers your question if that's what's been bugging you. So we can figure out the probability of what's coming next, but we don't have a way to identify what song we're in without temporal pooling. So in HTM theory, we think this happens in a pooling layer above where this is happening. That's why we always draw, in the current theory, we'll draw two layers. We'll draw one like this, and then we have this circuit we think is repeated twice in the common cortical column. Down in this one, we'll have SP, like spatial pooling, so we'll have mini columns and cells per column, temporal memory essentially running. And I'm going to call it TM, but it's the mechanism of temporal memory. It's only temporal memory when we're distally connected to ourselves, right? Sorry, I was ignoring chat for a bit, but I'll get back to that. And this one we want to pool. We want to pool and form an object representation based upon the activity of this over time. So assuming we have attention to one thing, like we're within the reference frame of one object. Let's say it like that, because those are the terms that we're moving towards it in a minute. I'm talking about reference frames. So assuming that we're defining one reference frame, an object's reference frame. As we move through that reference frame, that's what's happening here, moving through the reference frame, this is narrowing down to form a representation that we can match against things we know. Okay. Mark says there'll be repeated tone sequences. Yeah. Definitely. But doesn't it learn those transitions in the context of all the previous notes? Yeah, but we only had two notes. We didn't have, what we're trying to match against was two notes. So those two notes have all these different possible beginnings, right? We don't know the beginnings yet. As we listen to more, that's when we can narrow it down completely and lock it in on a sequence and know exactly what sequence we're in. But we have to have more input over time. And that whole model doesn't involve movement. You can think of it in two ways, with or without movement, because there's two ways that your brain's input changes. I won't write that down. There's two ways your brain's input changes. One is that reality changes, the world changes, the state of the things change, or two, you move through reality. And so your brain has to decide where the line is, where that line is drawn between reality and your effects on reality. That's one of the things it learns. The neocortex, I think, has a big part of learning. That's the models that it learns over time has to incorporate that separation between reality and your effects of your movements on reality. What will be indicted is all possibilities that match the fragment that's observed. More samples or restricted choices won't necessarily start at the beginning. Yeah, exactly. Okay.